Hello guys, welcome again to another lecture. In this lecture, we're going to talk about procedures. So, you guys has maybe used C++ or even C, and you know about functions. So procedures in assembly is exactly the same concept as a function. So you can call it a function. Some other, languages call it subroutines or method. All such, concepts are exactly the same as the procedure. So again, it's like a function, something you're gonna use a lot, some part of the code that you're gonna use a lot. So you write once this code, and each time you want to execute it or use it, you just call it. For example, like a cosine. In C++, if you want to do cosine in any angle like cosine 30 or cosine 60 degrees, you write the cosine one time, the function that will return the cosine of the angle, and each time you're going to use it, you just write cosine whatever angle you want. So basically, a procedure is a group of instructions that usually performs one task, like for example executing cosine. Okay. Again, it's reusable piece of software that is stored just once in the memory. So you can call it million times, but it is the same procedure that will be called each time. So instead of writing, that for example, the cosine, I'm stuck with this example. If you're gonna use this cosine in your software, for example, 1,000 times, you don't need to write this exact software code 1,000 times. No, just write it one time and call it 1,000 times. Of course, the advantage is very clear here. It saves the memory space, and of course, it will make it easier to develop the software. The disadvantage is that whenever you call a subroutine, there is a kind of time overhead. Some procedures that you're gonna do or steps. These steps takes time. Okay, and we're gonna see why in the examples in the following slides, why we need some overhead, in order to execute, a procedure. In assembly, we need, of course, some keyword, some mnemonic, in order to call for this subroutine and return for it. Okay, and in assembly, we use call to call the subroutine and ret to return from a subroutine. Okay. Let's see the rules for writing a procedure. Okay, here is examples for the procedures. Okay, different examples. So for any procedure, we need first the name of the procedure or label. So you can say name or label, whatever you like. And in that case here, the first one, it's sums. In that one here, it's sum one. Okay. Also, you need the proc or bros, whatever you like to call it, directive. So this directive here at the beginning, okay, tells the assembler, I'm sorry, that this is, the beginning of a procedure. At the end, you have the return, which you return from the procedure. And of course, you have end B. Okay, this is like a template. So you have here name, you can name it whatever you like. Then you have proc. At the end, you have ret, and the end B, or end the procedure, basically. Okay. Then one important stuff here is that the proc, directive is followed by the type of the procedure. The procedure can be, two types: near procedure or far procedure. So just for a moment, near is intra-segment and far is inter-segment. So I'm gonna explain here. So basically, this procedure, will be stored somewhere. It will take, of course, some amount of bytes. Let's assume this is, the procedure. If it's contained in the same code segment of the program, this is near procedure. You are not going out of the code segment. You are still in the same code segment. This is near procedure. Also, if this is a memory, for example, and this is the code segment in here, and the procedure is outside the code segment, then this is a for procedure. This is very simple, definition. Also, to continue the rules, the near and the far, types of procedure can be, or directives here, can be followed by use or use statement. It's another keyword, okay? So use statement allows some number of registers based on the, the user definition to be automatically pushed into the stack and popped from the stack within the procedure. So, for example, here in that, example, the third example, basically, it's we have here a near, procedure, and we're gonna use BX, CX, and DX. So in here, basically the procedure will use the same registers, BX, CX, DX that the main program is using, and with their same values. So one might think that since you are going to outside the code segment, the registers may be missed or something, So in order to preserve the usage or the same values of the registers, use statement. Okay. So in here we're gonna use BX, CX, and DX with the same values that they were set in the main program. And we're gonna, add these three values into AX. Let's talk in details here about the near call. So the near call instruction is basically 3 bytes long, okay? Of course, when you call a procedure, you call it inside the main code, okay? So, and when we say 3 bytes long, that means this instruction call, whatever, call some label, call this procedure, is, stored with the main program itself. It's one line from the main program itself. And it takes 3 bytes. The first byte is for the opcode of the near call itself. Of course, the processor doesn't speak English. So basically here, there are some ones and zeros, with some combination that the assembler will understand that this means near call. Then, the second and the third byte are the displacement that will be added to the current IP, so or the instruction pointer, or the program counter, whatever you call it, so to go to the new location. So we know that the procedure is stored somewhere, okay? So we need to know the displacement in order to add it to the current IP to go to this, new location. Of course, whenever you fetch something, the instruction pointer will be pointing to the next instruction to be fetched. Basically, that one here. That instruction, whatever it is. And remember here, if the code segment is 1000, okay, let's assume in that case it's CS, the code segment, register has 1000. So basically, the physical address here means we shift left CS by 1, shift left CS. So this will be 10000. Okay, and we add the IP, so that will give us here 10003. So basically here IP, which is that points to that location, is equal to 10003 minus 10000, which is basically 3. Good. So IP for that location, for the instruction that is just after the call, is 0003. And the displacement is, here is the displacement. So the displacement is 0f ff. And remember, 0f is the most significant because this is the higher address, than ff because this is the least significant because this is the lower address. So the new procedure now can be deduced as follows. If you want to know the physical address of the new procedure, just add these together. So 0, 0, 0, 0 is 3. So f plus 3, f is 15, remember. 15 plus 3 is 18. 18 is 60 and is 2, and the remainder is 16. So 2, and we have a a carry of 1. 1 here means 16. 1 plus f is 15. 1 plus 15 is 16, which is 0, and we have a carry of 1. 1 again here is the weight of 1 is 16. 1 plus f, again 1 plus 15 is 16. 16 is 0, and we have a carry of 1. 1 plus 0 is basically 1. So the new IB, this is the new instruction pointer, 1002. So if you want to know the physical address of the procedure, shift left CS by 1 bit. So this is the shift left, and then add the new IB. So 20011 11002. If you cannot follow, the hexadecimal addition, you can just use, for example, online, just write online 0FFF plus 0003 in hexadecimal, and there are many websites that can do hexadecimal addition for you, and you're gonna see it's 1002 as we do here. Okay, so that's basically the new location. But after finishing this procedure, we need to go back to 1003. So we need to store the current IB before we basically change it by adding 0FFF. So for that reason here, whenever you make a call, you make some steps. One step is what we have done right now, is just adding the displacement to the current IB, then shift left CS and define the new instruction physical address. Okay, one last step to do is to save the IB of the instruction just after the call, so that when we finish the procedure, we go back to that location here. For that reason, we push the instruction pointer into the stack. So for example, if the stack pointer, the last location that was used in the stack was that one here, okay, AFFF, we're gonna push 0003, that one. Remember, the IB of that location is 0003, not 10003, because this is the physical address. The 10003 is the physical address, but 0003 is the IB here. So we need to store this IB into the stack. So we're gonna put 00 in that one here, and the 03 in that one here. And again, the most significant byte is in the higher address FA, and the least significant byte in the lower address SB. And remember, SB get reduced. So this is reduced because the stack is different from the main memory. The stack pointer get reduced when we push something into the stack. Okay. One last comment here is that since the displacement is 2 bytes, so the displacement is 2 bytes, which is basically 16 bits. That means you can, make a displacement with 2 to the power of 16 when all of them are ones. 2 to the power of 16 is basically 64K. But since 64K bytes, so you can jump up to 64K bytes. But since the procedure can be above, in a higher position in the code segment or a lower position in the code segment, okay, then you can, go up or down. So basically, you can go up by half, 32K bytes, or down by 32K bytes. That's why it's a positive or negative 32K. Good. The far call here is basically, this is the main difference. It's 5 bytes. Since it's far, then we're gonna go outside the code segment. For that reason, when we store, we need to store not just the IP in the stack, but also the code segment, register. So in here, this program stores, basically this is, the new location that the IP is pointing to. So the IP originally is 0005, because again, the code segment is 1000. Okay. So before we make the far call, we need to store CS, which is 1000. And the old IP, which is 0005. And we need to know the, the start location segment of the new segment that we're gonna go to, or the procedure is stored in, okay? And the displacement inside this, new segment. So we're gonna go to a new segment. So if, for example, this is, this is a code segment, this is another segment, whatever it is, maybe the data segment. Okay, so we need to know the address of the first location of that new segment. This is the address of the new location. So the address is, the least one, basically. So 1100. And the physical address of that one shift left by one digit. So it will be 11000. And we're gonna make a displacement by 0002. So the physical address of the procedure is basically 2 here, 0011, 11002. Good. This is very important, of course. Of course, I'm gonna ask about this in the, in the homeworks, exams, So you should basically, review a lot, the far call, the procedure of the far call, what is, the, CS, what is IP, what is the new location on your new segment, first location address, what is the displacement. You should, comprehend, and understand this very, accurately. We can do also calls with register operand. So basically, till this moment, we just, when we make a call, we do, for example, call sums. Like, for example, the first, examples. So the name or the label of the it was called sum. So the name of the, or the label of the procedure was sum 1, sum 2. Okay, but we also can, call and based on the address of the sum procedure. For example, here we have a procedure called display meaning. Okay, so the label here is display. So, and it do something. So here in the main program, so this is the main program. And this is a procedure. So in the main program here, we store the address of the subroutine disk into bx. And then here we make call bx. So we do exactly the same. Again, we're gonna go directly to bx, and what's inside the bx? What's stored inside the BX is the, the physical address of the DISP, subroutine. Basically, if we go to this location, if for example, here we are using BX, this will be BX. Ret or return. So when we do the return, we said that return is used to still the the symbol that the procedure is ending here. But we actually do ret here because we need to go back to the exact locations that we should after the code. So here is the code, for example, the first example that we explored, which was near code. It was 3 bytes, and we said that the IB originally is 0003, which is basically pointing to that location. Okay, so when we reach ret here, the assembler knows, okay, this is the end of everything of this procedure. Let's now go to the first instruction after the code. For example, this is the first instruction after the code. To give you, a clear, this is the first instruction after the code. So when we execute this program, we're gonna execute this first, then that guy, then we go here, execute that guy, and then we do the return. The return will lead us to move the L and the letter or alphabet K. So ret here will do this, or when the assembler sees the ret, will do that. Basically, it will fetch or pop the old or the original IB from the stack. And once you have this, you know where to go in order to fetch the next instruction. That's it, guys. Thank you very much for watching, and see you in the next video. Bye-bye.